Hello, all you physics meisters out there. It's Physics40S with Dr. Carroll. This is Tuesday, March 24th. This is the first class about Unit 5, which is work, energy, and power. Some good stuff. Today we'll focus just on work, mechanical work, electrical work, lots of homework. So I'm going to use our mini text for the beginning, and this is on page 320. Something got cut off there, didn't it? Section 9.2, work, the transfer of energy, and you see someone pushing against a wall and the wall's not moving. The story of my life. So we have here that work is the transfer of energy. Now look here, I'm going to have a little line. Look at that. Oh, I got a blue highlighter there. I just discovered that thing. So work means so much in different contexts, but we want to stick with the physical definition. So you do work to transfer energy. If you're lifting a weight, you are increasing the potential energy, the energy of position of the barbells by hoisting it over your head. Okay, so when you do a force, apply a force on an object and cause the object to move in the direction of the force, that is an example of doing work. Work is the vector dot product of force and displacement. Now, as you take more university classes, you'll learn more about vector analysis and how you can take two vectors and multiply them together to get a scalar, which is what work is. There's also something called a vector cross product where you get a vector. So you'll learn all about that a little later. We can also write it, you see it as F delta dot delta D. I can also write that. That also equals to F delta D. I should make the pen smaller. Cos theta, where theta is the angle between the force vector and the displacement vector. The units of work are joules. That is the SI unit of energy. And work, as we'll see, is a change in energy. So it's going to be in joules. Work can also be expressed as newtons times meters. So a joule is a newton times a meter because force is in newtons, delta D, the displacement, is in meters. So we have here some construction workers. In the right-hand side on figure 9.4, worker A is pushing a wall that isn't moving, while worker B is pushing a wheelbarrow that is moving. So work depends on displacement as well as force, so only worker B, it's worker B is doing work, worker A isn't displacing the wall, therefore no mechanical work is done. No work is being done on the wall if the wall is not going to move. But worker B is moving the wheelbarrow forward, so the product of the applied force and the displacement gives me the work. Okay, so let's try some examples here. Let me get my calculator. Okay, calculator on. Calculate the work done by applying a force of 830 newtons forward on a 3,000 kilogram car to displace it 25 meters forward. Okay, so everyone sees this example here that I'm looking at. Give it a little circle. Oh, there you go. So all you're going to do is you're going forward, so my theta, my angle between the force and displacement vector is 0. And the cosine of 0 from your unit circle that you're all experts on in math is 1. Cos of 0 degrees is 1. And so I get F delta D, so that's going to be 830 times 25. Notice that I didn't even need to use the mass of the car. I already knew the force and I know the displacement, so multiply them together and I get the 20,750 joules that you see over here. Okay. Now the second one says we're applying a force to a 0.4 kilogram puck as it slides along a frictionless surface from rest to 10 meters per second in 0.2 seconds. So my force is 20 newtons. I just got to get the displacement. Again, I'm not going to use the 0.4 kilograms. Don't use the masses here. Don't do F equals ma because this whole business about instantaneous forces versus average forces. So use the given force, 20 newtons, times the displacement. So let me scroll to part B here, and I see that delta D is average velocity delta T. I'm going to make my ballpoint pen size smaller here. There you go. And so circle it there. So delta D is V average delta T. So your initial velocity was 0, final velocity is 10, average of that is 5 times 0.2 seconds is 1 meter. So my work is 20 newtons times 1 meter, or 20 newton meters. So 20 newton meters, or 20 joules of work is required to move the puck from initial to final point. Okay, and let me scroll up. And again, if you're stuck about it, pause, look at it again, still don't get it, send me a note on the magical Edsby. Okay, I don't know if it's really magical. There's a third one here. I don't think I've ever done this. Lifted a 57 kilogram outboard motor a distance of 1.4 meters from the ground up to the box of a pickup truck. Okay, so you're fixing a boat or something and you want to lift up 57 kilogram mass, deadlift up to a pickup truck. So my displacement is 1.4 meters. I assume I'm lifting up, not an angle, but straight up, because it didn't tell me otherwise. So I have to get the force. Now I got 57 kilograms, and I'm fighting gravity. So my force is going to be mg. It's going to be 57 times 9.8. Let's see if that's the case here. Yeah, oh, look at that nice picture. I'm going to circle that picture. Isn't that nice? Okay. I was in a movie once where I sat in a pickup truck. So there I am, from the 1950s. No, I wasn't in the movie in the 1950s. I was in the movie around 10 years ago. But the setting of the movie was the 1950s. Okay, you must know that. So I'm going to take the mass, 57 kilograms, times 9.8, and that's going to be my force. And there's even a free body diagram over here that shows all that. So 558.6 newtons, multiply that by the displacement, and I get 782 joules. So the work required to lift the outboard motor onto the box is 782 joules. And so that's good. Okay, let's do some more here. Just check that I'm still recording. Yeah, okay. Let's jump straight to example 2, where we're off at an angle. So, in your mini textbook, this is on page 327. 327, that is correct. Okay, so here's someone, newspaper carrier, choose your favorite newspaper. You're pulling a wagon at 275 newtons at an angle of 45 degrees to the horizontal. Okay, so that's east, 45 degrees north. How much work is required to move the wagon 8 meters? Now you might say, oh, can't we have theta 0 degrees? Well, that would be very uncomfortable for you to be sort of like crawling along the ground, pushing a wagon of newspapers. You have a handle, which means you can stand upright and carry those newspaper wagon forward. Of course, it is only the horizontal component of your force which is being used to propel the newspaper forward, but that's what we mean. I mean, it's F delta D cos theta. F cos theta is your F of x, right? Fx, your horizontal motion. So that's good. And then a question about a bicyclist. We'll get to that in a second. So, oh, why is that still on? I don't want that on anymore. There we go. The force and displacement are not in the same direction, but 45 degrees apart. So all you do is work is F delta D cos theta. So 275 times 8 times cosine of 45 degrees, and you get 1560 joules. Alternate method, you see here, you could take 275 times the cos of 45, so that's your horizontal displacement force, your horizontal force times the displacement. It's the same thing. You get 1560 joules. Good? Everyone's got that? I'm looking down all the rows of the hundreds and thousands of students I have in class. Oh, everyone's paying good attention. That's good. Okay. Question B. Calculate the work done on a cyclist if a braking force of 40 newtons slows the cyclist from 20 to 50 meters per second in 2 seconds. So here I am applying a force opposite to the direction of motion so I can slide down, and that's 40 newtons. My displacement, well, I go from 20 to 15 meters per second, so that's v1 to v2 in 2 seconds. So I can get the average velocity times the time displacement and put it all together. But let's be careful about our signs here. So I think I said v2 minus v1. I meant v2 plus v1. So the average velocity is 35 over 2, which is 17.5 times the time. So 35 meters is how many meters I'm going. But because the cyclist is braking, she's applying a force that is in the opposite direction to her displacement. Therefore, the angle between her force and her displacement is 180 degrees. So you take 40, 35 times cos of 180, which is -1. So the work done on the cyclist is negative 1400 joules. The value for work is negative because the force and the displacement are in opposite directions. So they're opposite directions, it's going to be negative. So that's how that one works. Work from an F delta D graph, we're going to omit that. So power we'll get into next lesson. Let me just see here if there's some work questions you can try on your own. Remember, at the end of the mini text there is an answer key. So let's keep going here, and there we go. On page 369, what questions shall we try here? These are end of chapters question. Let's try 21. Okay. Why don't I write this down? No. You got it. Page 369, number 21 and 24 about snowplows, and 28, 21, 24, 28. I want to do one off on an angle, maybe on page 370. Those were all straight. Page 370. Well, they really don't want to give us any ones on an angle, do they? Okay, well, there's also a work package which we'll look at later, but you try those ones for now, and we'll continue next time. Sounds good? Okay. See ya.